Okay, hi everyone. Today I am going to explain about what is the voltage regulation and efficiency of a short transmission line and how we will draw the phasor diagram and what is the equivalent circuit diagram of that short transmission line. Okay, that will be explained in present class. Okay, in the previous class we already discussed about the short transmission line. We already discussed about a brief introduction to the short transmission line and also what is meant by the efficiency and what is the definition for that voltage regulation are also discussed. Okay, next coming to the contents of this class. First one is the introduction to the short transmission line. First one is the introduction to the short transmission line. Okay, what is meant by the what is meant by short transmission line and how it is called as the short transmission line and what are the parameters are added and what are the losses are obtained for that parameters, that all will be discussed in this content. Okay, next one is the equivalent circuit diagram of a short transmission line. Okay, what is the equivalent circuit diagram of that short transmission line and what are the parameters are added for that equivalent short transmission line. Okay, that all will be discussed in the equivalent circuit diagram of a short transmission line. Okay, next one is the phasor diagram of a short transmission line. Okay, this is the very important one in the case of a short transmission line. Okay, how we will draw the phasor diagram. Okay, by using that phasor diagram we derive the voltage regulation and also efficiency. By using that phasor diagram we derive the voltage regulation and efficiency of a transformer. Okay, these are all the contents that will be discussed in present class. Okay, in that first one is the introduction to the short transmission line. Okay, what is meant by the short transmission line? The short transmission line means the length is less than 80 kilometers and the voltage levels are below 11 kV or 33 kilovolts. Then it is called as the short transmission line. Okay, the length of the line is less than 80 kilometers and the voltage levels are also below 11 kilovolts and maximum 33 kilovolts. Okay, that is known as the short transmission line. Okay, for the less length of the line the capacitance value will be neglected. Only in the case of short transmission line we are adding the resistance and inductance values. Okay, in a short transmission line the shunt conductance and shunt capacitances are neglected. Okay, in the case of a short transmission line the shunt conductance and shunt capacitance are neglected. Okay, because of small leakage current the capacitance C and the conductance G are neglected. Okay, due to the small leakage currents. Okay, next, only in that short transmission line the series resistance and inductive reactances are to be considered. Okay, in that line the series resistance and inductive reactance are to be considered. Okay, the series resistance and reactances are taken as the lumped parameters. Okay, series and shunted reactance are taken as the lumped parameters, not distributed parameters. Okay, for the easy calculation purpose we are using the lumped parameters instead of distributed distribution parameters. Okay, then the calculations for that short transmission line is simple when compared to the other lines. Okay, the equivalent circuit for the short transmission line is a simple AC circuit. It is just like as a simple AC circuit. Okay, this is the introduction about the short transmission line. Okay, understand? Next one is what is the equivalent circuit diagram of short transmission line. Okay, in the case of a short transmission line, the parameters are the only resistance and the inductance. This is the only resistance and also the inductance. Okay, the capacitance C value will be neglected due to the leakage of currents. Due to the leakage of current, the capacitance value will be neglected. Okay, this is the transmission line, single phase transmission line, and this is the neutral point. This is the phase line and this is the neutral point. This is a source voltage. This is the source voltage and these are the loads. Okay, mostly we are using the inductive type of loads. Okay, this is the sending end voltage. Vs is the sending end voltage. Okay, next one is the Is. Okay, Is is the sending end current. Okay, next I is the current flowing. These parameters R and X are the resistance and reactances of this short transmission line. Okay, this is the overall equivalent circuit diagram for the short transmission line. Okay, next the R and X represents the resistance and inductive reactances to neutral. Okay, the R and X are the resistance and inductive reactance to the neutral. Okay, next one is the I. I is the current in one conductor. Okay, I is the current in the one conductor. This is the I. Okay, is the current in the one conductor. Next one is the VR. Okay, VR is the receiving end voltage to the neutral. Okay, next one is the VR. VR is the receiving end voltage to the neutral. Okay, next one is the VS. Okay, VS is the sending end voltage to the neutral. Okay, Vs is the sending end voltage to the neutral. Okay, next from the equivalent circuit, this is the equivalent circuit diagram for the short transmission line. Okay, from the equivalent circuit, the receiving end voltage VR. Okay, from this equivalent circuit, the receiving end voltage VR equal to Vs sending end voltage minus I into R plus Jx. Okay, VR equal to Vs minus I into R plus Jx. I into R plus Jx. Okay, Vs is the sending end voltage and VR is the receiving end voltage. The sending end voltage is not equal to the receiving end voltage due to the presence of this resistance and reactance. Due to that resistance and reactances, there is some impedance drop will be obtained. Due to that impedance drop, the receiving end voltage will be reduced when compared to the sending end voltage. That receiving end voltage is reduced. Vs is not equal to the VR due to the presence of this resistance and inductive reactance. Okay, therefore VR equal to receiving end voltage VR equal to Vs minus I into R plus Jx. VR equal to Vs minus I into R plus jx. Okay, where R plus jx is the z, where R plus jx is taken as z. Okay, z is the impedance. R plus jx is replaced by the z. Okay, therefore VR equal to Vs minus I into z. VR equal to Vs minus I into z. Okay, this is the equivalent circuit diagram, and receiving end voltage, that is the equation number 1. Okay, where Iz is the voltage drop along the line, where Iz is the voltage drop along the line, where Iz is the voltage drop along the line. Okay, next coming to the phasor diagram, of a short transmission line. Okay, next coming to the phasor diagram. Okay, this is very important topic in the in this unit. First, taking the I, that is the load current as a reference. Taking the load current I as the reference. Okay, that will be denoted by the OE. Okay, the load current I is denoted by the OE. Okay, taking I as a reference. This is the I load current is the reference. Okay, that is denoted by the notations O and E. By the notations O and E. Okay, where I lacks the V due to the inductive nature. I lacks the V by an angle of phi r. Okay, by an angle of phi r, that I lacks the V. Okay, that is notated by the OA. Okay, VR is the receiving end voltage. Okay, where I lacks the VR by an angle of phi r. Okay, where by an angle of phi r due to the inductive loads. Okay, the loads are the inductive. Therefore, the I lacks the VR by an angle of phi r. Okay, that is notated by the OA. Okay, that is notated by the OA. Due to the resistance in the equivalent circuit or a transmission line, a resistive drop obtained. Okay, that resistive drop is parallel to the load current. Okay, the resistive drop IR is parallel to this load current. Okay, this is the IR resistive drop. Okay, that is notated by the AB. Okay, where AB is the resistive drop. Okay, that is the IR. Okay, next at an angle of 90 degrees, inductive reactive drop is obtained. At an angle of 90 degrees, inductive reactive drop is obtained. Okay, that is denoted by the BC. Okay, Ix is the inductive reactance drop. At an angle of 90 degrees, we draw the BC line, that is the inductive reactance. Okay, the sum of this IR and Ix is notated as the Iz. Okay, the sum of this IR and Ix is notated as the Iz. Okay. This triangle is the impedance drop triangle. Okay, understand, this triangle is the impedance drop triangle. By adding this impedance drop triangle to the receiving end voltage, we are obtaining the sending end voltage Vs. Okay, by adding this impedance drop to the receiving end voltage, we obtain the sending end voltage, that is the Vs. Okay, that is the Vs. Okay. Next we draw the Vs by an angle of phi s. Next we draw the Vs This is the sending end voltage by an angle of phi s. Okay, understand? By adding this red drop to the VR, then we obtaining the OC line. By adding this drop to this VR, then we obtaining the sending end voltage. Next, at an angle of phi r, taking the point as the A, at an angle of phi r, we extend this VR. Up to H point. And at an angle of phi r, at the center of the C, then we draw some line that is notated by the K. Due to that some conductance value, it will be represented as the small line. It is denoted by the G. Okay. Next, AG is called as the IR cos phi r. AG is notated as the IR cos phi r. Okay, next, GH is notated as the IX sin phi r. GH is notated as the IX sin phi r. And we project this A value to the E point, to that load current point, then it is notated as the D and is named as the VR sin phi r, and it is notated as the VR cos phi r. OD is represented as the VR cos phi r. After that, we project this B to E point. Okay. This is the overall phasor diagram for the short transmission line. Okay. This is very important diagram. Next one is taking I as a reference phasor, where I lags the V. Okay, due to the inductive loads, the I lags the V. Okay, then OE is the load current and OA is the receiving end voltage, and AB is the resistive drop, and BC is the reactive drop, and AC is the line impedance drop. OC is the sending end voltage Vs. Okay, OC is the sending end voltage Vs. In that, OE is the load current. And OA is the receiving end voltage. Okay, and AB is the resistive drop. Okay, and BC is the reactive drop, and IZ is the impedance drop. Okay, next OC is the sending end voltage. Okay, this is the notations for the phasor diagram. Okay, from the phasor diagram, or by using this phasor diagram, we calculate the voltage regulation and efficiency. Okay, by using this phasor diagram, the sending end voltage, Vs is the OC. Okay, the sending end voltage Vs, this is the sending end voltage, is the line indicated by the OC. Therefore, OS equal to the OC, where OCF is the triangle. Okay, where OCF is the triangle. Okay, we know the formula for the hypotenuse square equal to the opposite side square plus adjacent side square. Okay, that means OC square or OC equal to square root of OF square plus FC square. Okay, OC square is equal to the square root of OF square plus FC square. Okay, hypotenuse square is equal to the opposite side square plus adjacent side square. Therefore, VS equal to the OC, that is equal to the OF square plus FC square. Fc square. Okay. Next, in that phasor diagram, we observe what is the OF. Okay, OF is equal to the OD plus DF. Okay, OF is equal to the OD plus DF. Next one is the FC. Next one is the FC. Okay, FC is equal to the FB plus BC. Okay, FC is equal to the FB plus BC. Okay, next coming to the OF. OF is equal to the OD plus DF square. Okay, the notation for this OD is the VR cos phi r. The notation for this OD is the VR cos phi r. Okay, what is the notation for DF? Okay, DF is the length of this DF is equal to the length of the AB. Okay, the length of this DF is equal to the length of the AB, that is the IR. Therefore, DF is equal to the IR. Then OD plus DF is equal to the VR cos phi r plus IR. VR cos phi r plus IR. Next coming to the FC. Okay, FC is also write as FB plus BC. Okay, FC is also write as FB plus BC. Okay, the length of this FB is equal to the AD. Okay, then it is also notated as the VR sin phi r. Then it is also notated as the VR sin phi r. Okay, next one is the BC. Okay, the BC is the IX, that is the inductive reactance drop. Okay, BC is the IX, inductive reactance drop. Therefore, FC is equal to the VR sin phi r plus IX. VR sin phi r plus IX. Okay, this is the triangle OCF. Okay, this is the triangle OC and F. Okay, the formula for the hypotenuse is equal to the opposite side square plus adjacent side square. Okay, what is the opposite side? That is the FC. What is the opposite side? That is the FC. Okay, what is the adjacent side? That is the OF. Okay, the FC is also write as OD plus DF square. Okay, understand, FD is also write as OD plus DF. Okay, and also FC is write as FB plus BC. FB plus BC. Okay, the OD is notated by the VR cos phi r. And what is the notation of DF? Okay, the length of this DF is equal to the length of the AB. The length of DF is equal to the length of AB. Okay, the length of this AB is notated by the IR, that is the resistive drop. Okay, therefore the notation of this DF is the IR. Okay, therefore OF is equal to the VR cos phi r plus IR. OF is equal to the VR cos phi r plus IR. Next coming to the FC. FC, what is the FC is equal to the FB plus BC. FB plus BC. Okay, the length of this FB is same as the length of AD. Okay, it is notated as VR sin phi r. Therefore, FB is equal to the VR sin phi r. Okay, next one is the BC. Okay, BC is notated as IX, that is the inductive reactance drop. Inductive reactance drop. Okay, therefore FC is equal to the VR sin phi r plus IX. VR sin phi r plus IX. Okay, understand? Next, okay, this is the equation number 2. Vs is the OC, sending end voltage. By using the triangular formula, then hypotenuse is equal to the square root of adjacent side plus opposite side. Hypotenuse is equal to the square root of adjacent side plus opposite side. Okay, OF square plus FC square. OF is equal to the OD plus DF square, and FC is equal to the FB plus BC square. FB plus BC square. Then OD is equal to the VR cos phi r plus IR. FBBC is equal to the VR sin phi r plus Ix. That is in equation number 2. Okay. Next, sending end phase. Sending end phase, that is the phi s. We write the tan phi s by using the triangle. Okay. We write the tan phi s by using the triangle OCF. Apply the tan phi s value. Okay, what is the formula for the tan? Okay, tan equal to the opposite side by adjacent side. Opposite side is the FC. Okay, the adjacent side is the OF. Therefore, tan pi s equal to FC by OF. Okay, tan phi s is equal to the opposite side FC by adjacent side OF. Adjacent side OF. FC by adjacent side OF. Therefore, we know the value for the FC. FC is equal to the FB plus BC. Okay, FB is the VR sin phi r plus BC is the Ix. BC is the Ix by OF. OF is the OD plus DF. Okay, where OD is the VR cos phi r and DF is the IR, and DF is the IR. Okay, therefore, next one is the sending end power factor. Next one is the sending end power factor, that is the cos phi s. What is the formula for cos phi s? The formula for cos phi s is the adjacent side by hypotenuse. Okay, adjacent side means the OF. Okay, what is the value of OF? OF is the OD plus DF. OD plus DF. What is the value of OD? VR cos phi r. Okay, next one, what is the value of DF? Is the IR. Okay, therefore OF is the VR cos phi r plus IR by OC. OC is the sending end voltage by Vs. Sending end voltage by Vs. Okay. This is the sending end phase. Phi s equal to tan inverse of FC by OF, that equal to VR sin phi r plus Ix by VR cos phi r plus IR. OF is the VR cos phi r plus IR. FC is the VR sin phi r plus Ix. Okay, that is the equation number 3. Next one is the sending end power factor, that is the cos phi s. Okay, the cos phi s is the OF by OC. OF by OC. OF is the VR cos phi r plus IR by OC is the Vs, sending end voltage. Okay, it is the equation number 4. Okay, next, the percentage voltage regulation. We already know the percentage voltage regulation formula. Okay, that is Vs minus VR by VR. Vs is the sending end voltage and VR is the receiving end voltage by VR. In terms of percentage means we taken as into 100. Okay, we already calculated the what is the value of Vs, that will be calculated in previous. Okay, this is the Vs, square root of VR cos phi r plus IR whole square plus VR sin phi r plus Ix whole square. Okay, this is the formula for the Vs. Okay, that formula will be substituted in this case. Then the percentage voltage regulation is write as square root of VR cos phi r IR square plus VR sin phi r Ix square. Okay, sorry, in that we are having the VR also. Okay, minus VR. By minus VR by VR. Okay, this is whole divided by VR. Okay, in that VR missed, that's why I write the minus VR. Okay, this is the percentage voltage regulation formula. Next, to determine the approximate value of sending end voltage, that is the Vs, OA plus AG plus GH. Okay, that also we will be observed in the phasor diagram. Okay, that is also we observed in the phasor diagram. Okay, first, what is the approximate value for the sending end voltage? Okay, the sending end voltage is the VOC. Sending end voltage is the OC. Okay, OC is approximately equal to the VR while taking as VR is equal to the OH. Okay, OH means VR is approximately equal to OA plus AG plus GH. Okay, OA plus AG plus GH. In that, OA is the receiving end voltage VR. OA is the receiving end voltage VR and AG is the IR cos phi r. Okay, and GH is the Ix sin phi r and GH is the Ix sin phi r. Okay, that is the approximation equation of the sending end voltage. If there is no parameters, then in that case only the resistance is, the sending end voltage is equal to the receiving end voltage. But in the case of transmission line also, due to the resistance and inductive parameters, we are obtaining this drop, impedance drop. Okay, while considering the approximation equation for the sending end equal to receiving end, then we taken as OA plus AG plus GH. Okay, what is the value of OA? OA means the receiving end voltage. And what is the notation for AG? AG is the IR cos phi r. Okay, and what is the notation for GH? GH is the Ix sin phi r. Therefore, Vs is approximately equal to OA plus AG plus GH. That means VR plus IR cos phi r plus Ix sin phi r. IR cos phi r plus Ix sin phi r. Okay, that is the approximate equivalence for the sending end voltage. Okay, Vs is approximately equal to the OA plus AG plus GH. OA plus, okay, AG plus GH. OA is the VR, GH is the IR cos phi r, AG is the, GH is the Ix sin phi r, AG is the Ix cos phi r. Okay, that is the equation number 6. Okay, therefore, the percentage voltage regulation is equal to Vs minus VR by VR into 100. Substitute this Vs value in this equation. Then we are obtaining VR IR cos phi r plus Ix sin phi r minus VR. Okay, substitute this in this equation, then it is the VR plus IR cos phi r plus Ix sin phi r minus VR. Okay, by VR into 100. In terms of percentage, it will be taken as into 100. Okay, in that VR gets cancelled. Okay, in that VR gets cancelled. Then we obtaining IR cos phi r plus Ix sin phi r. By cancel of these VR terms, then we obtaining IR cos phi r plus Ix sin phi r. Okay, by VR into 100, by VR into 100. Okay, this is the equation number 7. Okay, this is the last voltage regulation formula for the transmission line. Okay, this is the voltage regulation formula for a short transmission line. Okay, where IR is the resistive drop and Ix is the reactive drop and VR is the receiving end voltage. Okay, this is the overall voltage regulation formula for the short transmission line. Okay, by using this formula, we calculate the how much amount of voltage regulation are obtained in the case of a short transmission lines. Okay, if the voltage drop will be very less, then it gives the more advantage. Less voltage drop give the more advantage. Okay, that is the overall derivation for the voltage regulation. Okay, next coming to the efficiency. Okay, next coming to the efficiency of a transmission line. Okay, we already discussed about the what is meant by the efficiency and what is the definition for the voltage regulation in previous class. Okay, first of all, what is meant by the efficiency? Okay, efficiency of a transmission line is defined as it is a ratio of power delivered to the load to the power supplied from the sending end. Power delivered to the load to the power supplied from the sending end is known as the efficiency of a transmission line. Okay, the delivered power to the supplied power, it is the ratio of delivered power to the supplied power is known as the efficiency of a transmission line. Okay, the delivered power is the receiving end power. Okay, we already know what is the formula for power. Power equal to the VI cos phi I. Okay, the formula for the power is the VI cos phi I. Okay, the delivered power means the VR IR cos phi r. Okay, the delivered power means the VR IR cos phi r. Okay, to the supplied power is written as delivered power plus losses or line losses. Delivered power plus line losses is known as the supplied power. Okay, delivered power plus line losses. What is the formula for delivered power? The delivered power is the VR, IR, cos phi r plus line losses we consider as resistive line losses, that is the I square R losses. Okay, that is the I square R losses. Okay, this is the efficiency of a short transmission line. Okay, this is the formula for the efficiency of a short transmission line. Okay, that is the it is the ratio of delivered power to the supplied power. Okay, it is the ratio of delivered power to the supplied power. Supplied power is also write as delivered power plus losses. Delivered power plus losses. Okay, where VR, IR, cos phi r is the voltage, current and power factor at receiving end. Okay, where VR, IR, cos phi r is the voltage, current and power factor at the receiving ends. Okay, next one is the VSIS cos phi s. Okay, VSIS cos phi s is the voltage, sending end voltage, IS is the sending end current and cos phi s is the sending end power factors. Okay, this is the efficiency of a short transmission line. Okay, by using this efficiency formula and by using this voltage regulation formula, we calculate the what amount of voltage drop and what is the percentage of that voltage regulation and what is the efficiency of that transmission line will be easily calculated by using these formulas. Okay, that will be easily calculated by using these formulas. Okay, by using this equivalent circuit diagram and the phasor diagrams, okay, we draw the phasor diagram and then we observe how we will calculate the voltage regulation by using this formula. Okay, that all will be related to that phasor diagram only. Okay, in the case of a short transmission line or medium transmission line, the phasor diagram is the one of the very important consideration. By using this phasor diagram only, we derive the formula for the voltage regulation. Okay, this is the short transmission line. Okay, by using this short transmission line, we transmit the power from the generating station to the substation. Okay, we transmit the power from the generating station to the substation. Okay, while transmit this power, how much amount of voltage drops are obtained and what is the efficiency while transferring of this power, that all will be calculated by using this phasor diagram only. Okay, by using this phasor diagram only, we calculate the voltage drops and also efficiency Okay, this is the main important consideration and in the case of a short transmission line. Okay, these are the various parameters and this is the how we will calculate the voltage regulation. That all will be discussed in previous one. Okay, this is the voltage regulation formula and this is the approximate voltage regulation for that transmission line. Okay, that will be only approximately equal to the OA plus AG plus GH. Okay, the notation for the OA is the receiving end voltage and AG is the IR cos phi r and GH is the IX sin phi r. Okay, this is the normal voltage regulation formula. Okay, by cancelling of this VR terms, then we obtaining the overall voltage regulation formula is the this. Okay, this is the overall voltage, percentage of voltage regulation. Okay, this is the formula for the percentage voltage regulation. Okay, this is the formula for the percentage voltage regulation. Okay, that is the percentage of VR. Percentage of VR equal to IR cos phi R plus Ix sin phi R by VR into 100. By knowing this formula, we calculate easily what is the percentage voltage regulation that will be obtained in the case of a short transmission line. Okay, in that IR is the resistive drop. Due to that resistance, how much amount of drop will be obtained? Due to the presence of this inductive reactance, how much drop will be obtained? And VR is the receiving end voltages. That all will be calculated by using this formula. Okay, next this is the overall efficiency formula, that is the power delivered to the power sending, power delivered to the power sending, delivered power plus drop, delivered power plus drop. Okay, this is the overall transmission efficiency and regulation in the case of a short transmission line. Okay, by using this efficiency and voltage regulation formulas, we easily calculated the how much amount of voltage drops are obtained in the case of a transmission line, and what is the sending end voltage and how amount of receiving end voltage will be obtained, and what is the efficiency of that transmission line. That all will be calculated by using these formulas only. Okay, these formulas are used for calculating the percentage of voltage regulations and the transmission efficiency. Okay, this is the calculations of the transmission efficiency. This is the voltage regulation formula, and this is very important formula for calculations of this voltage regulation. And also this is the efficiency of the overall efficiency of this transmission line. Okay, these two formulas are very useful for calculation, and also we understanding the performance of transmission lines. Okay, by using these two formulas, we calculate the regulation and efficiency of the transmission line. Okay, by using this formula, we observe what is the voltage drops are obtained, how much amount of voltage drops that will be obtained in the case of a transmission lines. Okay, that all will be calculated by using these formulas, and also we calculate the how much amount of voltage will be sent and how much amount of voltage that will be received at the receiving ends, and what is the voltage drop due to the resistance and reactive parameters. That all will be calculated by using these two formulas only. Okay, by using these two formulas, we easily calculate the efficiency and the voltage drops or the percentage voltage regulations. Okay. Okay, thank